Good afternoon, and thank you for joining us for our webinar today on de-risking microgrids and distributed energy resources in Australia. My name is Tricia Fitzpatrick, and I'm the marketing manager at Homer Energy by UL. We are very happy that a large group of people have joined us today, and we are looking forward to getting our presentation started. We do have a very full agenda for you as we explore the importance of de-risking microgrids and distributed energy resources in Australia. We'll look at mitigating risk over the life cycle of a project, from system design to safety, and how those impact the ability to finance an installation. We're fortunate that today's presenters bring a great deal of expertise. Since Homer Energy was acquired by UL in December of 2019, we now have access to expertise that covers many areas of a project. Our presenters today are Dr. Peter Lilienthal, who is the Global Microgrid Lead for UL and a founder of Homer Energy, Farhad Molahagahi, who is the Head of Country in Australia and New Zealand for UL Renewables, James Trudeau, who is the Global Business Development Manager for Integrated Energy Systems at UL. James is responsible for energy storage systems and e-mobility, and is the former founder and CEO of a lithium battery firm that focused on energy storage systems. And David Menser, who is UL's Head of Microgrid Advisory Services. David spent the better part of 4 years bringing smart module solar into the marketplace in Australia, and that was eventually bought by SunPower. And then moderating the Q&A session will be Dr. Marilyn Walker, who is Global Lead of Hybrid Power Systems at UL Renewables and a founder of Homer Energy. In today's presentation, Farhad Molahagahi will share his perspective on the growth and need for microgrids and DER systems in Australia. Peter Lilienthal will present the importance of design and the role of solar and storage. Then James Trudeau will explore the benefits and risks of energy storage. And David Menser will examine risk mitigation in terms of the bankability of a project. And then Marilyn Walker will be collecting your questions over chat, and then we'll join to moderate the Q&A session. So now let's get the presentation started. I'd like to welcome Farhad Molahagahi to begin our presentation. Farhad?
Yeah, thank you, Tricia, and thank you everyone for joining this today's very informative webinar. I do hope that you do enjoy listening to my dear colleagues about the microgrids and de-risking for Australia. Before I start, I would like to pay our respects to the traditional landowners, past, present, and emerging of this land. And equally, I would like to have a safety moment and ensure everyone is safe, well, and healthy in these challenging times. So, and as we sort of talked about safety, it is very important that I do wish to reiterate the fact that, in fact, we take great pride in UL in harnessing and nurturing and maintaining our dues when it comes to safety. This is simply our mission. And in fact, for over 125 years, we've been working together to make sure people are safe in terms of products they use and places they live and work. Next slide, please. So a little bit about UL Underwriters Laboratory. Here in this slide deck, we have a timeline representation of UL's journey to date since it was founded in 1894. As you can see, in the century and decades since its founding, UL has stood the test of times while countless good organizations have come and gone. Our journey in becoming one of the world's leading experts in renewable energy started in the early 80s. And as you can see from the timeline, we have continuously maintained our growth and aspiration to grow and to be the market leaders in renewable energy sector, providing both certification and technical advisory. Next slide, please. Our global presence, as you can see from this slide deck, spans over 140 countries with offices in every corner of the globe. We service and provide top quality, bankable advice to some of the world's leading renewable energy projects. Next slide, please. A team specializes in providing a range of services from establishing market compliance to providing Tier 1 independent engineering technical advisory, covering wind, solar, energy storage, e-mobility, as well as other emerging technologies such as green hydrogen. We work together with major manufacturers, owners, developers, lending institutes, super funds, and investment corporations to provide assurance on their investment with minimal risk. Next slide, please. Microgrids. So why Australia? A rapid uptake of renewables, the increasingly high cost of extending a centralized generation network, and soaring diesel prices make distributed energy systems like microgrids an appealing option for Australian energy. With bushfires, flood, and cyclones events becoming more frequent and severe, electricity supply challenges during and after these events are becoming more and more significant. Electricity dependence during these events also heightens the risk and consequences of physical and cyber attacks, highlighting the need for local energy solutions like microgrids and other forms of hybrid energy generation systems to becoming a viable solution. Smaller scale and tailored microgrids can accommodate larger amounts of renewable energy. Australian renewable is currently expanding 10 times faster than world's average per capita. Over the 2019 and 2021 period, Australia pipeline for new wind and solar system is roughly and approximately around about 7 gigawatts. Australia has the highest solar uptake in the world, with rooftop up to 50% a year. The rapid implementation of renewables continues to a larger shift towards distributed energy resources, with the energy landscape now consisting of household energy storage systems, electric vehicles, demand response, and energy-efficient appliances. Consumers are driving the demand for connected series of hybrid generation systems. Next slide, please. Here we can see news headlines taken from various media outlets showing the ever-evolving need for hybrid energy projects. What it's primarily saying is that it's boosting local economies. Microgrids can serve local regions by generating economic value and creating jobs, which is a pertinent issue in the post-COVID-19 climate. It promotes self-reliance, i.e. it allows you to generate your own electricity to accommodate your own needs, and it does save money, and improves operations and increases resiliency, and it does help organizations to meet their sustainability goals. Next slide, please. So how can UL help? This slide illustrates a project lifecycle and key elements involving during this process. With that, UL simplifies the complex process of determining the lowest cost of energy for microgrid and distributed energy systems when considering multiple technology. We are capable of modeling any combination of energy generation and storage technology. We help simulate and live data to design the most optimal solution that is suitable to the project needs, and provide sound financial support assessment along with developing state-of-the-art operational practices. With that, I now hand over to Peter. Thanks, Peter.
At Homer, we've been doing designing hybrid systems for over 25 years, starting in 1992 at the National Renewable Energy Laboratory. It was an offshoot of commitments that we made at the Earth Summit in Rio. And it's changed a lot over those times, and I won't go through all of the changes, but in 2009, we spun off from the lab as a commercial entity, Homer Energy, with the exclusive license, and we've been enhancing it ever since. So in 2014, we came out with Homer Pro, and so a few years later, we came out with Homer Grid. So we keep enhancing it as we go. At this point, it's become a de facto global standard. Over 250,000 people have used Homer around the world. Over 100,000 have opted into our hybrid system design network, get our monthly newsletter and other information from us, and I encourage you all to sign up for that. And the map there shows where systems have been modeled using Homer, and you can see it's quite global. Australia is very well represented. We have over 3 million Homer files, and there's over 75,000 dots on that map that you see. Next slide, please. So let me explain a little bit about how the software works. Obviously, you need input data, economics, things like interest rates and load profiles, the site-specific renewable resources, and we have a library of components with data on all kinds of models of batteries and inverters and et cetera. And we also have data bases that you can log into to get load profiles and renewable resources. So there's lots of options for or import your own data. So those are the inputs. Then the software simulates the operation of a system hour by hour or minute by minute if you've got that kind of data, either for 1 year or for an entire project life. To tell how would one system work, how much fuel would it use, when would the batteries charge and discharge, when would components need to be replaced, et cetera, and what would be the total operating and life cycle costs, levelized cost of energy of that system. That's one system. And it does that for hundreds, maybe thousands of different systems to optimize and find the least cost system to meet the requirements of that site. And so that tells you what's best, but it tells you what's best for one scenario. And a lot of times there's uncertainty. The finance community hates risk and uncertainty. So we've built in an automated sensitivity analysis that allows you to see how does that, how do those answers change if conditions change. So you can do sensitivity analysis on almost any of the inputs. And of course, it spits out outputs like your what's the optimum size of the different components, like the PV array, the battery bank. How are they going to perform? You can drill down and see how they operate hour by hour, and and what's the IRR and levelized cost of energy, et cetera, of the project. And we have a new proposal writer that produces a proposal that a developer could present to their clients. Next slide, please. So, why hybrid systems? And the answer is pretty simple. Solar and wind don't stand on their own. They need to be part of some kind of system. So if it's connected to the grid, it's part of the grid, and it uses the grid's dispatchable generation. For isolated systems, that's usually diesel, batteries, or batteries, or both. And there's lots of choices about how to design hybrid systems. This schematic that you're looking at here is a DC coupled system, but it could be AC coupled, and there's lots of design trade-offs because you've got multiple components. And that's one of the things that we really focus on, is helping customers understand those design trade-offs. Next slide, please. So there's many types of hybrid systems. We got started really focusing on isolated systems because that's where the cost of energy is highest and the need for renewables is greatest. But solar and batteries and the technology has matured and gotten cost effective enough that it's now competitive for grid connected systems. And we distinguish 3 different types of grid connected systems: edge of grid, behind the meter, and what we call front of the meter, which are the utility scale projects. So I'll talk more. Next slide, please. I'll talk more about each of those on subsequent slides here. So isolated systems, Australia has a lot of them. It's kind of unusual for a developed country to have so many remote applications, such as Aboriginal villages, huge mining sector, and your livestock stations, and some of them are obviously very remote and can't be grid connected. So when you look at these isolated systems, some of the biggest design issues are, can you go to 100% renewable? Everybody would like to do that, and we found it's feasible, and we do see that happening mostly in very small systems where you can do pretty aggressive load management. It's not really practical to have batteries for multiple days of poor resource, so you have to be able to manage your loads. So for larger systems, that's typically not so practical, and so they'll have a backup system. And in fact, most larger systems already have an existing diesel. So then the issue is, what kind of control upgrades do they need, and how reliant are you going to be on that diesel? Is it just going to be a backup for the poor resource times, or is it going to function as the backbone of the system? And that depends on lots of factors like your load profiles, your economics, and your project objectives, et cetera. So that's the next slide, please. So that's the isolated systems. Let me talk about some of the grid connected systems now. And edge of grid is almost uniquely Australian in that you've got in Australia many existing distribution lines that run for tens of kilometers and have a very low loads out at the end of them. This creates substantial problems with things like voltage support, line losses, and reliability. Those lines are vulnerable and they're hard to maintain. Putting a hybrid system out on the end of that system can solve a lot of these problems, give you that reliability you want, give you that voltage support, and reduce those line losses. So that's a very interesting application for these hybrid systems. Next slide, please. What's really taking off enormously in the US and in Australia, actually all over the world, are what we call behind the meter systems. These are systems on the premises of an energy using facility. This happens to be a food warehouse in the state of New York. There's multiple benefits here. Obviously, public messaging is good, but the PV, the solar, is good for reducing the energy charges, but by itself, unless it's in a hybrid system, it's not going to reduce the demand charges significantly, and it's not going to improve the reliability against short outages or the resilience against major outages. So, and we've seen a lot more of them. Both Australia and California have suffered from wildfires that have resulted in multi-day outages. So that's where resilience becomes really valuable. And these hybrid microgrids, they're grid connected normally, but they are capable of keeping the loads and the businesses operating even when the grid goes down. So that's what we designed the Homer Grid software for. Next slide, please. Right now, we're really starting to focus on these utility scale systems, these what we call front of the meter systems. This is because solar and wind are now the least cost form of electricity. But as I said in the earlier slide, they don't stand on their own. And even for these big utility scale systems, batteries can be helpful in a lot of ways. One is simply if there's an interconnection limit, or just to fill the interconnection and the feeder from the solar park at a higher capacity factor. So you can overbuild the solar, charge the batteries when the solar is producing more than the interconnection limit, and then discharge and improve the capacity factor by selling power in the evening. So that's become much more common. In fact, it's actually things like that are required now by many of the power purchase agreements and other contractual requirements. There's also a growing problem, and it's gotten the name of the duck curve, because that graph on the right kind of looks like a duck, where in the middle of the day when the sun's shining, you've got a minimum loading problem where the rest of the system can't back down enough. And then you've got this ramp problem. You can see on that red curve how steep it is when the sun sets. And batteries can solve both of those problems. So that's where you're starting to see a lot more batteries in these systems, but it adds complexity. Next slide, please. And complexity requires more analysis, and that's what we're for. It's help people understand that and overcome that complexity, and help you design these hybrid systems. The more components you have, the more degrees of freedom you have. So what's the how big should the PV be is no longer the only question. How big should the battery be? You've got tariff structures and contractual structures that sometimes are quite complicated, but that's what drives the economics. There's regulatory issues. I have already mentioned reliability, but I can't stress it enough how important that is, and how solar alone doesn't give you that reliability. A hybrid system does. So there's, as I said in the beginning, and it's worth repeating over and over again, is how many different trade-offs there are when you're designing these systems, and it requires substantial analysis. And also how important risk analysis is, mitigating and minimizing risk. So that's why we've created the sensitivity analysis that's built in. And next slide, please. I'm going to hand this over to James Trudeau in a minute. He's going to talk about one of the most important risks, which has to do with battery safety. That's so crucial to bankability. David Minster will follow that with a discussion about bankability and the financing of these projects. So, James, it's yours now.
Thank you, Peter. Good afternoon, everybody. Speaking to you from Texas. I'm going to cover a pretty broad overview of what energy storage is. Most of us know, but energy storage can be electrical, chemical, mechanical. There's a lot of ways of storing energy. One of the most common just 20 years ago was pumped hydro. But right now, lithium-ion batteries provide over 95% of the energy storage mechanisms in the marketplace. That's the most common thing you're going to see. And typically that's going to be an NMC or an LCO type chemistry. Energy storage can serve loads ranging from small homes to mini grids to large utility scale projects as Peter just described. Now, internationally, the definition of what energy storage is changing. A few years ago, we knew that energy storage was your big container like you see at the bottom, or a small home system like you see to the right. But the international fire codes, that's the IFC 2021 or the NFPA 855, the fire people gotten real concerned, and any system bigger than about 20 kilowatt hours, that's like a small 2-drawer file cabinet. Anything bigger than that is now considered energy storage. And so all the safety issues that go with energy storage are now being addressed all the way down to systems at that size. Next slide, please. There are great benefits when it comes to energy storage. Obviously, as Peter's been talking about, it enables the wider use of renewable energy, that's solar, wind, and it reduces the variability of renewable energy. If the wind stops blowing or is variable, or clouds go over your PV array, batteries can help smooth that. As an old utility engineer, variability on your generation's not something you like to have. So batteries are really good for that, and they provide additional stability to the electric grid, both in voltage and in frequency. A nice thing about energy storage is it enables the broader use of microgrids, and those are extremely important, not only in remote, cattle stations someplace, but we're seeing it increasingly in just a college, a school, a commercial complex. Microgrids are becoming really important as we take renewables down to the premise level. So in doing it, as Peter laid out with a very nice photograph there, it does improve the reliability of the power system for end users. Now we're seeing, and there are people, I'm sure, on this call, not just from Australia, but from the greater South Asian area. You've got a lot of places where the traditional electric source was a diesel generator. Well, using a microgrid with energy storage can take that cost of energy from a US dollar, about half a dollar US, down to 15 cents, and even less depending upon your scale. So it's, in doing so, it obviously reduces costs, but it also allows the reduction of ground and air pollution as well. Next slide. With great benefits, though, come great risks. In the last few years, we've had 28 major energy storage fires in South Korea. When I say major, think $1 million or more. Next slide. Not long ago, we had an explosion of an energy storage system for Arizona Public Service. That building right there is nice and square until it basically puffed out due to an explosion from batteries. And 4 firefighters were hurt. One of them was standing right in front of the door. He got blown through that chain link fence about 25 meters. Battery gas, when they start to fail, is about 40% more explosive than propane. So this is a risk, but we can deal with that. Next slide. To get a feeling for this, the little green cubicle right there, you could put that in your hand. That's 25 small little batteries called 18650s. And we overheated just one in the middle. When it caught fire, it got very energetic. When standard, that's what we call an NMC type lithium battery, goes in the thermal runaway, it burns at about, depending upon the model, between 1200 and 1500 degrees Celsius. The more difficult part of that is it produces its own oxygen. If you were to drop that burning battery thing in a bucket of water, it would continue to burn. Next slide. So what does that mean from a safety perspective when it comes to an energy storage system, like, for example, the container you see over in the bottom right? Let's do some math. A single 18650 cell, which is about the size of your finger, has about 10 watt hours of energy in it. Those 25 cells that you saw, that's only about 250 watt hours of energy. Now, a typical module, and I want you to think of a rack, because what happens typically, we have a rack, we have multiple modules screwed into that rack, but a typical module's got about 5,000 watt hours. A typical rack, about 10 modules. So a typical rack, just a single rack, has over 200 times more energy than the cells that you saw in that video. A typical container, like you see off to the bottom right, has over 3,000 times more energy than the 25 cells in the video. That's a risk. It comes with the great benefits. So how do we handle that? Next slide. Because we are definitely going to handle it, because we need energy storage. Our approach is what we consider a 3-layer approach. And I'm using US codes here, but Farhad and his team can help you with what the applicable codes are in Australia or in the surrounding countries in the Southeast Asian area. In the United States, installation codes, National Electric Code or the NFPA 855, these are the codes used to say this is how you can do something. Now, the codes will call out a standard. Okay, we want batteries to be safe and tested, so we want the batteries to be tested to 19, our code is UL 1973, and we want the whole system to be tested to UL 9540. That's critical, by the way. A lot of the primary cause of all those fires in Korea, if I had 10 pieces that come together to make an energy storage system, if they don't all talk to each other and pass alarms back and forth, if they're not cooperating with each other, we call that a failure of functional safety. That's a key word. UL 9540 tests for that functional safety so that we know all the pieces and parts are living in harmony and are doing what they should be doing. Now, when you install a system, we believe, it has a potential of going bad. It probably will never do it, but has that potential. So good engineering is going to look at the testing and say, okay, show me what would happen if it does fail. Then the smart engineers in the world can look at that data and say, okay, therefore I'll space it this way. We'll put in these mitigating factors for sprinklers or whatever else we need to do to deal with not an unknown threat, but a measured quantity of threat that makes it, now I can engineer safety into the system. Next slide. So it's all about risk mitigation. That means I'm not only operationally, but I'm also I'm looking at financial risks. Homer is going to help you with that. Operational and performance risks. You don't want to install all this money in a hybrid system and then not have it producing the benefits you needed. We've identified, it's obviously safety risks. These things can get nasty on you, and the environmental risks as well. Bottom line is all of those risks can be measured, mitigated, and dealt with good codes, good standards, good project oversight. And that's where Farhad and his team come in, and accurate modeling. That's where our Homer software comes in to manage all this. That's why UL has brought all those pieces together, because we want a full solution set for our customers. Now, all of this is nice, but it all comes down to dollars in many cases, and David is going to handle that for us. David, it's all yours.
Great, thanks, James. I'm really glad you pointed out the risk elements in making sure that the batteries, and I'm sure it's the other critical equipment as well, is tested and it's validated and it's performing as stated, and that all of which is safe to use for their intended applications. It's just so crucial. My name is David, and I head the Micro Advisory Group, where most of my time and focus is in collaborating with developers, IPPs, and financiers, and to help them make sure that their projects are economically viable. It's a good complement to what James does on the testing side. And as James noted, I'll focus a few minutes of our time on financing microgrids, DER systems, which are code for behind the meter, and much of the same of what I'll go through in the next few minutes applies to utility scale systems as well. The situation is that the systems are complex. The applications are super diverse. The costs are very real. Most of the systems are financed, and yes, even here, the financiers and the capital markets supporting these platforms, they have a refined process, right? And so one of the challenges in executing our projects is in de-risking the project for the finance community to move forward, and so that they can place their investment comfortably, easily. So identifying, assessing, the frequency, the probability of negative impacts, the prioritizing and treating the risks is essential. It needs to be well thought out for that finance community to support. What else? Deep techno-economic tools are required, no doubt. And thus far in my now 15 years, Homer's been the only tool that financiers have found to be bankable. One recommendation when working on a project to support this part of the decision-making process and to capture the financial investors' support is begin designing the system with this sort of a platform early on. Homer provides that backbone and the analysis, and not only because of the many degrees of freedom that are available to design the system, but the same approach is key to the de-risking itself. So based on the application, the goals, the site specifics, even funding, Homer can formulate a good, solid, efficient design and provide not only accurate cost estimates on the CapEx or the initial capital, but as well as the ongoing operations and maintenance expenses, and then return back what the savings looks like, what the revenue returns look like. There are a number of parameters or measurements that the tool provides that allows us to figure out which configuration is the most optimal for this particular situation. My goal in the next slide or two is to share an overall framework for managing these risks and how Homer supports it. Next slide, please. Right, so once the application and the project goals are understood, it's time to design a system with these major system components and functions that need to support. And irrespective of the business case and the environmental conditions, there are functional risks, particular to the system equipment, that have to become integrated, and they have to become assessed, and especially those that are safety related. One of the best ways to pull all this together is in using the design tabs from Homer, and I've got a little wire, SLD-like schematic to the right, which includes wind, solar storage, diesel. And when we do it this way, we can run different sizes, we can run different architectures in parallel, we can optimize for costs or savings or returns. And the other thing that helps pull all of this together is that Homer has a rich library of the manufacturer's components in a sort of a drop-down approach. And so you don't have to go searching very hard. In fact, it's quite easy to integrate that particular component and the performance of that component into the system. But back to risk. What's especially important to financing is the ability to run sensitivity analysis on just about everything. And we call these what if scenarios, right? What if the PPA has an escalation? What if it doesn't have an escalation? What if the rates change? What if the rates change at some particular time? What if demand charges go away or they increase? We could apply the same to the cost of diesel. What if diesel increases in its price or decreases? All of which can also be applied to OpEx. On the battery side, we worry or we get concerned about excessive wear out, and this too is something that we can model with the sensitivity analysis. Next slide, please. Right, so once the sensitivities and risks are identified, organize them. Understand the impacts, break them down into those you need to avoid because the probability and the impacts are high. Transfer them to a third party, reduce, and then always reduce, right? And then those that you're left with are more likely the ones that you're going to have to tolerate, but then hopefully at this point you're tolerating those with low probability and low impacts. From a finance perspective, from a financier's perspective, they like this by no small amount. Now, they might not need you to have to run every possible permutation of all the sensitivities and all the risks, but they are going to ask you to harmonize all these risks throughout the project lifecycle. And one of the best ways to do this is in this classic risk matrix. What's the likelihood of something taking place? What's the impact? What do we do about it? How do we avoid? Do we transfer to another party, such as an insurance agency who may carry warranty insurance or performance guarantees, or even a revenue shortfall policy? Reduce everything you can as much as possible, and then live with what's remaining. Let's see. Next slide, please, which is my last slide. Okay, so we have limited time together today or this morning, but I did want to share just one view of Homer and how we use it, right? For example, here's a situation with a microgrid using wind, diesel, solar storage, and how we can apply some of the risk analysis techniques from the previous slide. In the level 1 category, the situation is we want to avoid high impact prices, issues due to price variability of diesel. And this could be directly related to the host's ability to generate profit to pay off the loan, which then from a financier's perspective impacts the DSCR, the debt service coverage ratio. So one way to manage this, one way to look at this is to run a sensitivity analysis on the cost of diesel and that price variability. Perhaps the cost of solar or energy storage is unclear, and you can run one-in scenarios for the same reason and to avoid unnecessary surprises. In the level 2 category, this is where we just want to transfer it to a third party. It's technology, it's performance, it's construction risk, it's resource availability, it's unpredictable demand. There's a lot of risk here that we can actually transfer to another party. On the resource side, it could be wind is unpredictable or intermittent, or we're in a cloudy area. Homer lets you run that analysis and lets you determine what the exposure looks like. In the level 3, perhaps we find that maintaining the equipment and the ongoing operations, the OPEX is a concern. What's nice about this view is you can see the contribution of the OPEX and by component and begin the process of reducing it quite easily. Lastly, you know, some of the things that you're going to have to tolerate are truly outside of your control. It's environmental, it's force majeure, theft is also a consideration, and these just might be things that are also above and beyond your normal means to manage the situation. Let's see. That was my last slide, so I'll leave it with thanks again for sharing some time together and listening to how one could de-risk projects using Homer's software. That's all the prepared material I had, so I'll pass the mic over to Farhad for some final thoughts.
All right, thank you, David. So I suppose just to sort of recap and reiterate, we talked about that there is certainly a clear trend and increasing demand for hybrid power systems across Australia. However, for these projects to get funded, they need to be safe and sustainable. In order for a project to be safe and sustainable and bankable from a technical perspective, today we learned 3 key items that should be considered. So Peter touched on the project design that should be sort of meet the needs of the user as well as meet the needs of the funder. James talked about the battery safety, it being a crucial for a project for the longevity and for it to be safe. And he demonstrated very clearly how that is very important and a key important part of the project. And finally, David talked about, from the project developer's perspective, demonstrating the project risks that needs to be identified and how they need to be mitigated. So with that, I will pass that on to Tricia. Tricia, thank you.
And thank you, Farhad, and thank all of you for a very excellent presentation. Before we go to questions, I do want to address one question that often comes up, which is how do I get started? There are several ways you can utilize UL's expertise. You can use Homer software to model your microgrid and find the least cost solution, and you can download it. You can download our Homer Pro software for a free trial at homerenergy.com/trypro. If you've already had a free trial, you can renew your trial to get more experience. And to help you dive deeper into the program, we also offer premium support and training. If you would like help with your with modeling your project, you can contact support@homerenergy.com, and our team can actually do the modeling work for you. And if you would like UL's help with the full scope of your project, then contact Farhad to learn more about UL's advisory services. So with that, at this time, we'd like to go ahead and go to questions now. If all the presenters would go ahead and please share your webcams, And Dr. Marilyn Walker has been collecting questions for us. I know there might have been some issues in the chat box, but hopefully, Marilyn, you've been able to collect questions. And what do you have for us?
Lots of great questions. So, and I actually see Peter might have typed some of them, but I'm going to ask them anyway so that they go out to the whole team and we can maybe have discussions on some of them. So one that we do get a lot, actually the first question that came in, how do you incorporate Australian tariffs into Homer? When this person used Homer the last time, it was mostly inclined toward US tariff systems. And Peter, you want to take that? You're muted. There we go.
I was reading the last question that came in. That was about how to incorporate additional tariffs that aren't in our database.
Yeah, how do Australians deal with tariffs? How should they deal with tariffs?
Yeah, no, so we have a tariff builder. There's a simple one and an advanced one. So it depends how complex your tariffs are. Check out the advanced tariff builder, and if it doesn't do everything you want, let us know. Either we for a very small fee, we can create a tariff for you. We do that frequently. But we also want to know how to improve our tariff builder as well. So check out the advanced tariff builder. We think it should work for most cases, but if it doesn't, we want to know about that, and we'll fix it.
Yeah, and that's also just to remind them that we did put in some free support into Homer Grids pricing so that you can get some engineering help with your tariffs if you need it, or anything else that you need help with. Okay, there was one. Oh yeah, what is the difference? I assume this was for you, Jim. What is the difference between NMC and LFP in terms of security and flammability?
Okay, so everyone understands, NMC is a cobalt-based positive side of the battery. Both of them use a carbon or graphite negative side, and LFP is an iron phosphate side. What starts the fire almost always in a battery is not the iron phosphate or the nickel or the cadmium or whatever it's in. It's the electrolyte. It's the liquid electrolyte. That's I'd say the match. So both of those batteries, both of those chemistries can produce, when they start going in an overcharged condition, the most common mode of failure, they produce a cloud of explosive battery gas. That's quite honestly, that's more dangerous than thermal runaway. Now, iron phosphate, the LFP, doesn't go into as energetic a thermal runaway as the NMC battery does. So, from safety, if I'm going to put an energy storage system in the middle of downtown Melbourne, I'm probably going to want to do LFP because that's a little safer, but it doesn't have the energy density that NMC has. So if I'm out in some cattle station somewhere and I need to save as much energy as I can, I'm probably going to use NMC. Bottom line, both of them are excellent. Both of them can cause fires. It's a matter of understanding the risks and trade-offs. And again, my toolbox has lots of tools in it. There's not one that does everything, and both of those are excellent chemistries.
Great, thank you. And we have quite a few questions here, 3 or 4 anyway, about peer-to-peer trading, blockchain, and what are our plans for that?
Well, you're the blockchain person, Marilyn.
Throws it back to me. Sure. Absolutely. There's absolutely a lot of potential for that. And I think that it's much more about figuring out the trading algorithms than the blockchain per se. So, and once that gets done, I don't know that will be our team that does that. It's not likely to be, but once that's in place, we'll certainly try to figure out how to model it, because I do think it's a really interesting modeling problem. But the actual trading algorithms and how those would work, to me, are the things. And yes, blockchain would probably be the right technology for that when you did. Okay, this is a good question, I thought. Do you see any issue in maintaining transient response of battery with fluctuating load? Does it restrict microgrids to residential load, or storage systems are even suitable for industrial loads?
No, batteries actually are much more responsive with less stress on the system than a typical mechanical system like diesel or some other spinning reserve. That's one of the beauties of batteries. Now you'll want to pick, obviously, how do I say this? Some chemistries are better at short duration events and some are better at long duration events. So you'll want to pick your chemistry or mix them together to accomplish that. But no, short duration things, it's wonderful. It's wonderful, for example, utility systems, frequency response and voltage support. These are measured in milliseconds and batteries do flawlessly on that.
They're actually better than generators.
Oh yeah.
Transient response.
Okay. Let's see, what was that one I was going to do? So what's the advantage of a hybrid system over just a solar system for demand charges, for dealing with demand charges? Why?
Well, you'd have to be really, really lucky for solar to really reduce your demand charge, because demand charge is created by the peak, typically 15 minutes but the peak 15-minute demand during the whole month. Is that in the evening? Is that when the solar is producing at its maximum? If you've got a lot of solar, it could easily be during a cloudy day. It's just, all you need is one 15-minute period. But batteries are dispatchable, so you can reserve their capacity for those peak periods. So it's definitely the case that to reliably reduce your demand charges, you need batteries. Solar is great for reducing your energy charges, but you need batteries or a backup generator, maybe, if you're allowed to do that. But batteries are what you need. Hybrid systems are what you need for demand charge reduction.
Peter, let me give an example.
Sure.
You're a manufacturer of some goods, and you have something that uses a lot of power, a forge, a stamping machine, whatever, but you only need to run it in the morning or the afternoon. It's an intermittent use thing. It's not constantly running. Batteries tied to that whole management system of that facility can effectively erase that demand charge from that nasty intermittent demand for welding or stamping machines or something like that, and they can do it much more effectively. And Peter is 100% right. Winds, solar, those kind of things are great for energy. Batteries are great for dealing with that power issue.
Right. And James, cement, aggregate, concrete manufacturing facilities are prime examples where there are very large loads that for very short periods of time, and then the trucks pull in, everything gets loaded, and then the trucks leave, and most of the facility shuts down waiting.
It also applies, it can be as simple as a hospital with an MRI machine, which puts a big load on it. So it doesn't have to be truly industrial. It can be a very technical load as well.
And something that we're going to experience more and more of as mobile batteries. We're talking about electric vehicles, right? Become more prominent worldwide. The batteries in those EVs are becoming larger, and the chemistry is such that they can be charged faster. So larger loads, shorter duration. I'm thinking of mostly DC fast charging systems for buses or any larger vehicle. That's going to have a very large impact on the local node or substation.
I think what you're going to see, the EV charging system of the future, be it a forklift for a warehouse or being at the cars at a school, that EV charging system of the future is going to be solar, batteries, connecting probably to an AC charging system, a level 1 or level 2. So get used to that. You're going to be seeing that.
So we're getting close to the top of the hour, and I'm sorry, Marilyn, I'm going to jump in because there's a lot of questions, and I'm going to summarize them about bankability and I thought I should really highlight the fact that now that Homer is part of UL, UL has advisory services and other software and has been in the bankability business, if you will, for a long time. And so it's not just a Homer thing. And maybe, I don't know, Farhad, if you wanted to talk about some of the advisory services and bankability reports that we can generate? Or
Yeah, thanks, Peter. So I suppose in terms of the bankability reports, yeah, we tend to sort of touch all aspects of the generation corner, looking at obviously not just unique to solar, but certainly to wind, solar and battery. And the bankability reports that we do provide certainly helps pave way for the developers mainly, and also the banks, if you like, to get the confidence that they require as part of their financing processes.
Great. Actually, before we end, I do just want to say, I want to put one question back because I know it's top of the hour, we should be done. But somebody asked, can V2G be designed in Homer? We can do EV charging right now. V2G is on the roadmap. But Farhad, could you talk briefly about the trends in Australia and Southeast Asia with regard to charging stations and what's happening?
So I think some of the bigger utilities are certainly currently talking amongst themselves in terms of putting up very rapid, sort of dispersing the EV stations. Certainly, you are seeing quite a lot of that in the shopping centres these days. But with the big utility companies such as AGL, Origin Energy, to name a few, Energy Australia, are now talking about putting rapid charging stations at various locations along the main strips of transportation routes. So it's a bit of a work in progress, if you like. With the bigger utility companies, power utility companies, certainly they are thinking about it. It is part of the future energy conversations that they are having. And essentially, there would be infrastructure that we'll need to see, and we will see in the very near future.
Great, thank you. So with that, I'm going to turn it back over to Tricia to just tell us how to get your questions answered and how to get support if we didn't get to it tonight, because we certainly couldn't get to everything.
Very good. Thank you so much, Marilyn. Thank all of you and your and to the audience for your excellent questions. Before we go, I do want to let you know what else is coming up. We do a lot to keep everyone abreast of developments in the hybrid power system market. We offer a regular program of educational webinars, and we also publish original news stories regularly. And to stay connected with these opportunities, you can sign up for our email newsletter on our news site, which is microgridnews.com. The webinar topics we have coming up are putting the power of Homer to work, which will show how your products or sales proceeds can be modeled in our application program interface. It's a tool that's used by so many applications like GE and Rolls-Royce MTU power systems. We'll also have a webinar to demonstrate modeling wind for island applications and a comprehensive webinar all about energy storage, the heart of the energy transition. So be sure to sign up at microgridnews.com. And thank you again for attending today's webinar. If you did not get your question answered, please send it in through your sales rep or our support desk, and we will respond. And watch for an email in the coming days with a recording of this webinar. And we hope to see you at our next event. Thank you.